Speak loudly. So, all right. So in the previous class, I left you with this problem. Build a machine that accepts or matches all and only the strings starting with fish. Here, the alphabet set is all the letters in English language. So how many of you finished this? Okay. No one from this side? All right. Okay. Yeah. So tell me. Yeah, you. So tell me how many states are there in this machine? 5. Okay. So let me list them. Two, S3, S4. And should I write the fifth state here? Okay. S5. And S1 is the start state. Okay. So now what the arrows should be? Huh? Can't hear you. So an arrow from S1 to S2 on input F. Yeah. Then? Okay. On input I, there is an arrow from S2 to S3 and S from S3 to S4. So H from S4 to S5. Okay, then actually, so let me write S5 here first. There will be a slight change. Okay. Now what? Anything else comes, it stays back where? No, that will not work. Um, so first of all, what is the accept state? S5? Yeah, silence please. S5? Okay. Now, what you are suggesting is, suppose here anything other than F comes, it stays here. Okay. Suppose if something, say A comes here. All right. Now, what will happen then? Even A fish will also be accepted by this machine, right? And A fish, or if I say A or B or C or any of them, then anything can come before fish. It can be BB, D, fish, whatever it is, that will be accepted, right? So that should not be accepted. So what to do? So far it is fine. Fish will be accepted, but fish should be the beginning. And so this should not be there. All right. And if such letters are there even in between, that will also cause a problem. Like again, I can say A, B, C, anything except I, J, K, L, up to Z. Okay, now again, other words will also be accepted, F, A, B, D, whatever, Z, and then ISH. This will also be accepted. This should not be accepted. So this is also not allowed, right? So what to do? Right, right. So we can take another state S6. So I will call it S dead. Usually it's called a dead state. Okay. So rather than staying in the same state for a different letter, it should go to this dead state. So any letter except F. So here we can say A to Z except F should go to S dead. Similarly here, once you come to S2, it means you saw an F. Now the next letter has to be I. If it is anything other than I, you go to SDED. Okay. So again, A to Z except I. Again here, S3 is expecting S. If you see any letter other than S, go to dead state. And here, if you see any letter other than H, go to the dead state. All right. After this, once you reach the final state, you can have any letter. It does not matter. It should start with fish. What it's ending is, it doesn't matter. So once it reaches S5, either fish is the only word and there are no more letters, that is also accepted. Or if there are any more letters, it doesn't matter what letters they are all accepted. So it remains in S5 for all the remaining letters, A to Z. Okay. Now, once you come to dead state, even here you should think, what if I get any more letters? Here, this is only speaking of one letter. Instead of F, if I get A or B, I come to S dead. But after that, I may get some other letters also, right? So once you reach S dead, it means you're not going out of this state. Usually a dead state is that which it's like a black hole. Once you come in, you can't go out. Okay. So once you reach this state, no matter what letters you get, until you finish reading the string, you loop in this state only. You don't get out of this state. Okay. So this is the formal automaton, finite automaton for accepting the words which start with fish and they may end with anything or whatever. They can't begin with any other word, or they can't have any other word in between these letters, fish. It has to begin with the word fish. So you see, whenever we speak of finite automata, although we are naming the states S1, S2, S3, and so on, each state actually has a meaning. Like here, dead state has a meaning, so we are naming it as dead. Later, we will see some examples where each state, we will try to name them meaningfully. Here also, each state has a meaning. Each state sort of stores the history of the string read so far. Like if you are in S1, it is understood that you haven't seen any letter so far. You are at the beginning of the string. You have not seen any letter. If you are in S2, it is understood that you saw one letter, that is F. If you are in S3, it is understood that you saw F and I. That's it, no other letters. If you had seen any other letters, you would have been in S dead by now. Since you are in S3, it means you pass through S1 and S2. And since you pass through S1 and S2, it means you saw F and I. Okay. And if you are in S4, it means you saw FIS. If you are in S5, it means you saw some word beginning with fish, because it's not that you just saw fish, because it is cycling in the same state. You may have seen some other letters as well, but you have seen fish to begin with. That much is clear. If you are in S5, you have seen fish plus maybe something else, but you have seen that. Okay. So each state here tells you what letters you have seen so far. If you are in SDED, it means somewhere you have missed. The sequence of fish you did not see. Where you did not see, it doesn't matter. Either first letter is not F and hence you came to SDED, or maybe first letter is F but second letter is not I, or maybe first two letters are F and I but third letter is not S, or first three letters are FIS but fourth letter is not H. One of these cases would have happened for you to land in SDED. Otherwise, you would not land there. That's all. So SDED does not tell you exact path in which you came there, but it tells you a broad idea of what happened, of why you came there. One of these letters is missing, is not in its place, expected place. F, I, S, H, they should be in that order. One of those letters is not found in the expected place, hence you came to SDED. That's what it says. Okay, so each state means something. The moment you are in that state, you know something. Okay, so all these words will be accepted by this machine, like fish, fishing, or some arbitrary non-English word may also be accepted. Fish, whatever, DK, DX, something. Even this will be accepted. But any other words like maybe food or mm, something, none of these will be accepted because they do not satisfy the condition that it should start with the word fish. Okay, these will be accepted. No, this checks only for one word. Yeah, we can. We will see later. So it's like you should have another state which takes a space or comma or new line as input. And then once you read any of those punctuation marks, you go back to the start state. Then this process will continue. Okay. Yeah.
So why is it S5 mapped to the dead state?
It need not. Once you are in S5, you accept a string. Dead state means you are sort of rejecting a string. Once you see fish, there is no reason to reject a string.
It's just a rejection.
Yeah, dead state is like a rejection string. And also you can't have two arrows for the same symbol. A to Z are already mapping onto S5. Again, you can't have A going to some other state. With any letter, A or B or C, you can't go to any other state. Yeah. At least in deterministic finite automaton. We'll see another automaton where that is possible. Same letter, you can go to two different states. Okay, so far we just saw examples and a brief idea of finite automata. So basically finite automata is nothing but a set of states and arrows between them. These arrows are nothing but the input letters. So if you have some M states, for each state you should say M states and N input letters. In the alphabet set, if you have N letters, then for each state you should say where it goes to on each of these input letters. So you will have M into N arrows. Okay, so this will give you the finite automaton. So now let's look at the formal definition of it. So formal definition of a finite automaton or a finite state machine. Okay. All right. An FSM is a 5-tuple M equal to Q, sigma, delta, Q naught and F, where Q is a finite set of states sigma is finite set of input symbols all the alphabet and delta is the transition function which defines the motion across states for specific inputs. So if you take this example, so here we can say delta is a function which takes two inputs, the current state and the current input, and it tells you the output, which state it goes to. All right. So suppose we say if you are in state S1 and you get input A, you will go to S1, right? So the inputs are S1 and A. The output will be if you are in S1, if you get input A, where do you go to? S1. Okay. Similarly, say if you are in S3 and if you get input B, where do you go to? S2. So if you are in S3 and you get input B, you go to S2 and so on. All right. Now, can you tell me what is the domain and range of this delta function?
The domain is the set of states and the Cartesian product with the set of alphabets. Range is going to be the set of states.
Yeah, that's it. So whenever you are asked for domain and range of a function, you can first take these kind of examples. Okay, how many arguments the function takes and what is the output of the function? Here the function takes two arguments and these are elements from some sets. All right. So you should see which sets these elements belong to, these arguments belong to. So the first argument comes from the set of states and the second argument comes from input symbol. So you need to take the cross product of these two sets. That will be your domain. And the output element comes from the set of states. So it will be a mapping. The domain is Q cross sigma and the range is Q. Okay, so this is how you understand the domain and range of a function. Always keep in mind the arguments are elements of sets, whereas the domain and range are sets themselves. So you should look at the arguments and understand which sets these arguments come from. And those sets will constitute your domain and range. Okay? All right. So here, delta is a function which maps from Q cross sigma to, what is the range? Q. Okay. And then Q naught is the start state. You see, I'm basically elaborating upon these five elements. A formal automaton is defined using these five elements. It's a tuple. It's a five tuple. And in the same order. Tuple means a sequence. Sequence means the order matters. Sequence and set, there is a difference, right? In a sequence, the order matters. So the first element in the sequence has to be the set of states. Second element has to be the alphabet. Third element has to be the function. Fourth element is the start state. Okay. So Q naught is the start state. And Q naught also belongs to Q, right? One of these states becomes the start state. One of these states is designated as the start state. And F is the set of final states or accept states. Can anyone tell me the relationship between F and Q? Yeah, F is a subset of Q. All right. Start state is always one. There is only one start state. And second thing, you should designate that start state. You can designate anyone as a start state. The way you can designate root of a tree. Similarly, here you can designate any state as a start state. That is up to you to choose. There is nothing inherent in a state that only this should be the start state. Okay. And second, F is the set of final states. Final state need not be one. It can be 0 or 1 or more than 1. There can be no final state also. It means the machine does not accept any string. Such a machine can also be there. All right. So there can be no final states or only one final state or many final states. But start state is always one. Final states can be many. So final states, F is a set of states which is a subset of Q. Some of these set of states are designated as final states. Okay. All right. So let's take an example and define it formally. So let's take this one. All right. So let us call this FSM as M1. So it's like machine 1. And M1 is a 5 tuple Q, sigma, delta, Q naught, and F. Right? So now let's define each of them. What is Q in this example? What are the states? Yeah, S1, S2, S3. Okay, and then sigma. We sort of defined it last time. A and B. Okay, and delta. So I need to specify the function. Now, what are the different ways in which we can specify a function? We can represent a function. Sorry? 3 into 2. What do you call that? We were discussing functions. I told you two kinds of representations. What are the two ways of representing a function? Set builder is for sets. Function is a mapping between sets. What are the two formats? One is a table format, right? Another is sort of a list. You take element by element, different possible inputs and their mapping, right? So first one, we make a simple table in which we list the states as rows and the input symbols as columns. So S1 on A goes to S1. S1 on B goes to S2. So that's what we write here. S1 on A goes to S1. S1 on B goes to S2. S2 on A goes to S3. S2 on B goes to S1. S2 on A goes to S3. S2 on B goes to S1. S3 on both AB goes to S2. Okay. So S3 on both A and B goes to S2. All right. So either we can represent delta like this, or we can also list all the possible inputs. So we'll get 6 different inputs, right? 3 states, 2 inputs, total 6 inputs, 6 arguments for the function. 6 pairs as inputs to the function: S1A, S1B, S2A, S2B, S3A, and S3B. Okay. So same thing, either you can look at the diagram or you can look at the table. So S1A is S1, S1B is S2, S2A is S3, S2B is S1, S3A is S2, and S3B is also S2. That's it. So these are the 2 ways in which you can represent any function. Same thing we are doing with delta also. All right. Okay. Now finally, Q naught is what? What is the start state here? S1, right? And then what are the final states? S2. There is only one final state, but F is a set. So even if you have one final state or no final states, you should always represent F as a set. So here you should put S2 in set notation. All right. Okay. Any doubts? And again, like I mentioned earlier, so in this notation, the first element comes from Q, the second element comes from sigma. Okay. Yeah, and the output element comes from Q. Okay. So we take the Cartesian product of Q cross sigma and map it to Q. So this is delta's definition. So this will be my domain and this will be my range. All right. Okay, so now let's look at some examples. Let's try to build some finite automata for different languages. Okay, construct. So you should try this. Construct an FSM which accepts only the string AB. That is, the language of this FSM is, it contains only one string AB over the alphabet A and B. I'll not mention the alphabet every time. Like I said earlier, assume the alphabet is just AB for all the examples which we are discussing. Okay. So now build an FSM, build a finite automata. Okay. So how many are done? Okay. Yeah, you tell me. How many states will be there? Three. Okay. Three or four? Four. Fourth one should I write here or here? Okay. Okay. S1 is start state? Yes. All right. Okay. If it's A, S1 goes to S2. Okay. Okay. S3 is the accept state. Okay. 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 What? That's it. S3 and SDED also you should say no. Yeah. What? S3 if it gets A or B, it goes to SDED. And SDED, if it gets A or B, it remains in SDED. So is it correct? It is correct, right? So whenever you are asked for this kind of example, first build the machine which accepts your example, then think of the remaining parts of the machine, remaining portion of the machine which rejects the remaining examples. Okay, so first think of those states which accept A, B. That's all. So first you are in start state, you read an A, okay, you go to S2, and if you get a B, you go to S3. Done. Accept. Now, what all cases this may fail? If the first letter is not A, then it may fail. The only other option is B. So if it gets B, go to SDED. And suppose the first letter is A, but if the second letter is not B, again it may fail. So you have gone to S2, first letter is fine, but the second letter may not be B, which means it is A. If it is A in S2, then you come to SDED. Okay, if both letters are fine, you reach the final state. But another condition is it should be only AB. Nothing should be there after that. So once you reach the final state, if any more string is still remaining, then again you come to the dead state. So you should not put a loop. There should be no letters after AB. It should end there. If there are still letters after AB, you should reach the dead state. And whatever more letters are there, you continue in the dead state until you finish reading the string. You just end there. That's all. Okay? Clear? All right. So always keep in mind, reaching the final state does not mean you have finished reading the string. Finishing reading the string is independent of reaching the final state. You may reach the final state before, or you may finish reading the string before reaching the final state. Anything may happen. Okay, both are independent. You should consider the case, what if there is a string remaining even after I reach the final state? You should consider all those cases also. Okay. So this will accept only AB. It will not accept any other string A, BA, AA, or ABA. None of these cases it will accept. It will accept only the first one, and all the others it will reject. Okay. It will reject, right? B, 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 you said. It's in S1. The moment it reads B, it goes to SDED. But it won't. That's why the starting state, yeah, only AB. It will accept, and it should accept only AB. This machine will accept only AB. The moment you just think, now the machine is given to you. Now you think what strings it will accept, what strings it will not accept. So if I give BAB, this is what you are asking? Yeah, you are in S1. You see B, where do you go to? SDED, over. Once you are in SDED, you see A, you again stay in SDED, again you see B, you again stay in SDED. That's it. So you can think of this step-by-step diagram. You can draw the diagram for your convenience. All right. This will also be rejected. Okay, one more example. So build a machine which accepts the language A, B plus. That is 1A followed by one or more Bs. Okay, so let's call this L4. So L4 will look like this. It will have AB, ABB, A triple B, and so on. Yeah, for all the examples we are discussing, sigma is A and B. That's all. Next, you guys should tell me the answer. You can do everything in mind, no? All later, some more big examples will come. Those also you do in mind only. Yeah, they are supposed to tell the answer now. Okay. Alphabet set is same. Unless I say it is different, it is the same alphabet set. Yeah. How many states? 3. Okay. This one, this 2. Third one, should I draw here or below? Below. Okay. Okay. S1 is start state. Yeah. Then on A, S1 goes to S2. A to S1. What do you mean A to S1? On B, it goes to S3. What about this? Will there be a symbol on the arrow to the initial state between S1 and S2? A. Okay. S2 to S. A. Okay. S3 will be a dead state. Okay. That's all. Is this correct? No. You tell. What same? When you don't maintain a notebook, you should never go wrong. Otherwise, you should maintain a notebook, not to keep in your lap. Yeah, you tell me. Okay, so this will be S4. There will be one more state S3. And what will this arrow be? B. Okay. Final state, accept state. Okay, if we get B, it will again go to S3 only. Okay. That's it. This is correct. Yeah, this is correct.
Except that on S1. Yeah, sorry.
It's correct. Yeah, because you need at least, yeah, if you want to discuss, either you go out and discuss or sit somewhere and discuss. So again, there should be minimum 1A. You see, you should behave as if you will get valid strings. First of all, in your mind as a machine, you should think, I am getting valid strings. So valid strings means it should begin with an A. Okay, I am getting an A. Then I go to S2. Then I assume I will be getting a B, minimum 1B. S2 can't be the final state because if that is the final state, it will accept A also, right? So I should get minimum 1B. Until then, I should not accept. So I get a B, minimum AB I get, and then I go to the accept state. Once I accept, now I will see what, so AB is accepted. Any other strings beginning with AB can be accepted? Yes, if they are followed only by B's. So once I'm in the accept state, the remaining letters should only be B's. As long as they are B's, I will remain in the accept state. The moment I see any letter other than B, I will reject it. So I will go to the dead state. Okay. Now at any of these steps, if I get a different letter, which is not in its expected position, I will go to the dead state. If the first letter is not A, I will go to dead state. If the second letter is not B, I will go to dead state. And once I reach the accept state, only until I get B's, I will remain in accept state. If I get an A, I will go to the dead state. That's all. Once you reach dead state, whatever other letters you get, you keep circling in the dead state only, looping in the dead state only. Okay? Any doubts? Okay. All right. Now, next one, A, B star. That is 1A followed by 0 or more B's. So this will have strings like A, AB, ABB, A triple B, and so on. So you see a relation between previous language and this one. So this language, L5, is nothing but L4 union A. So additionally, only one more string you are accepting, that is just single letter A. Okay. Now build a machine for this. Yeah. Okay. S1, S2, and S dead. S1 will go to S2 if the first letter is A. Okay. S2 is the accept state. There will be a loop on S2 if it is B. S1 will go to S dead if it sees B. S2 will go to S dead if the input is A. And S dead will loop on itself for A or B. Is this correct? Yeah. So the only difference between the previous one and this one is, in the previous one, we also had to ensure there is at least one B. Here, we need not worry about that. Here directly, even if we see an A, we can go to the accept state. And if we see one B or more B's or no B's after A, we are still in the accept state. Only if we see any other letter while in the accept state other than B, if we see A, we come to the dead state. Okay. All right. One more. Can we? Why do we need two final states? Okay. So what you're saying is here, if I make S2 as a final state, yes, that will also work. Yeah, good question. So only thing, we just need to take the previous machine, make S2 a final state. That will also work. Yeah. A good point. Okay, so let's quickly work this out. A star, 0 or more A's. Build a machine which accepts this language. So 0 or more A's means what? What strings does it accept? It accepts empty string, that is epsilon. It accepts A, AA, AAA, and so on. Okay, so build the machine. Anyone done? Okay. Yeah. Yeah. Sorry? Only S1 will be there. Okay. This is also accept state. All right. This is also the start state. Okay. Loop. Okay. Okay. So I'll just draw the red state here. That's it. Should finish this also, no? Yeah. Is this right? Sorry? No. If it starts with B, it goes to S dead. What do you mean starting with B? If first letter is B, it goes to some other state. S1 means before it read any string, before it read any letter. The moment it reads a letter, it goes to another state. Okay, so this is actually a correct answer. Yeah, so epsilon is not a separate character. The moment the start state is an accept state, it will automatically accept an input, accept an empty string. Start state means you haven't read anything. And even if you haven't read anything, you're accepting, which means you're accepting empty string. So epsilon is not a character which you are reading. Epsilon is inferred by making the start state an accept state. So by now, I hope you understood. Whenever a start state is an accept state, it will automatically accept epsilon, and vice versa. If you want to accept epsilon, just make start state an accept state. Okay, that's all. So let's stop here.